better deployment agility because everything is the same, so you don't have to learn different way of operating something. I think the biggest reason why virtualization is adopted for the cloud is because of the enablement for service innovation, right? Telcos and operators must innovate quickly with new services, and to do so, they have to do them themselves. So the notions of buying existing VNF or equipments and go to deployment with them, I think is a stopgap measure. Longer term, the ability to build up a developer base around your cloud network is essentially will be the determining factor between successful deployment versus not. Okay? So if you look at the promises of VNF, right, and full disclosure, I fully believe in this, right? You get the ability to write your code once and deploy it in many places. And to some extent, you can even have your own app store in the cloud. And trust me, many people have contemplated this idea. It's not new. And last but not least, there's no vendor locked in because everything is, quote unquote, built on open source and open projects. When I go to work in the morning, though, what I found is that reality is not a team player. I don't tend to agree with you in most cases, and you wrestle with all sorts of nuances and details with virtualization that poses a bit of a challenge to this vision, right? When you talk about VNF, I mean, is it VM or is it container? You know, what do you run on the host and the guest operating system? Do you deploy with Heat or Tosca? Or, you know, private or public cloud? And if you go with public cloud, which cloud? So on and so forth. Maybe you buy VNF from vendor A, would interoperate with VNF from vendor B. Okay, so these challenges are a bit of an obstacle in having virtualization and digital transformation being widely adopted in the telco cloud. So we posit that service portability is fundamentally the key enablement to solving this problem, right? It is a fancy way of saying we need to abstract design from the platforms, right? What does that really mean? When I talk about design, you know, I'm interested in algorithms. I'm interested in how I can service chain my services together. What sort of compute, storage, and networking requirement that I would need to go to deployment? What kind of scale do I need? How do I scale horizontally? How do I scale vertically? What sort of reliability I'm looking for? So those are immutable. Those are part of my design. They're not going to change regardless of which cloud I onboard my design onto. What you see on practical consideration is there's a lot of discussions and focus about what I call platforms, which is different kinds of clouds, different orchestration mechanism. How do you automate your deployment? What sort of storage do you use? Whether you should be using, you know, Linux from vendor A versus B. It goes on and on and on. As a developer, you know, I'm ambivalent to that. I just want to have a platform where I can actually take my design and deploy them on, right? So the enablement has to give me that capability. So let's talk a little bit about service chaining, what it really means. To me, service chaining is about drawing a dotted line between two functional elements. You know, whether those elements are at the granularity of data center or whether they're at the granularity of libraries of no consequences to me. Right? So if you look at sort of, you know, the entire service as a built, you know, as a series of concentric circles, at the very center, you've got these core libraries, starting with things like DPDK and VPP. You may even include things like the Intel Nav SDK as part of that core libraries, right? But then outside, I mean, but nobody wants to really write code from scratch, you know, against these libraries. You want something a bit higher level. You know, after all, this is 2018, right? So people often look for these type of component framework that can abstract these nuances for them and just simply assemble parts together into a complete solution, right? And so there are a few out there that has been well established. We have support for two at present. One is the click modular router framework that had been done over 10 years. It came out from UCLA. It was actually started by a guy named Robert Morris of the Morris fame, the worm, right? He actually was convicted for that, by the way. But anyway, it's a great framework for building router, but not just limited to router. You can actually use it to encapsulate just about any networking element and service chain them or connect them together to create something that are more consequential. Okay? Another framework that we're quite interested in is the P4 work that is spearheaded by I think it's Barefoot Network. While they designed P4 specifically as an enablement to their switches or the switches ASIC, we do see applicability for P4 at a higher level on par with what Click is doing today. So those are really nice way to encapsulate logical element from a networking standpoint and to servicing them together. But once you build an application in the context of a virtual machine, you also need to discuss the packaging mechanism, what I call services. So packaging is really about how you actually put this together. You know, whether you want to package them as a container, a VM, or to some extent as a Lambda function if you're going to deploy into AWS, right? That should be independent of the way that you build your application, right? Because packaging, think of packaging as compilation. You know, whether you're using GCC or LLVM, shouldn't really affect the way you write your code. Yep. And then, of course, you have different clouds, right? Now, you tend to not think about cloud from a service chaining perspective, but think about, you know, having your own private cloud with a certain amount of capacity, but it won't be able to handle, you know, peak demand. So you need to burst those overfill into a public cloud. And that dotted line between your private and the public cloud can be considered a service chain. Okay? So putting all of this together, actually, before we start, Michelle handed me this nice idea roulette, and it has a bunch of you know, different components and type of project that you can actually service chain together into a complete application. And what I'm going to show you is exactly how it's done in the real world. So got a bit of a video here because I don't have good luck with Murphy whenever I do live demo. But it starts out with the environment that we put together. And as you can see here, we load up a design, which is basically a logical design in a service chain fashion. This is actually a MEC application that we built. So you can zoom into the Evolve Packet Core implementation, and you can see that it is consisting of multiple smaller sub-elements, you know, the home subscriber network, the MME, and so on, right? And then you can go to the next level of abstraction, you know, which, by the way, you can configure these elements by clicking on them and specifying the property that they belong to. You can also go into the source code where they're implemented. So it takes you directly from the graphical visualizations of your design down to the implementation level. And what you're looking at really basically is a click implementation of that particular element. So you can come in and out of your design, and you can service chain them together very quickly to put together an application, a networking application. Right? Now, hold on a second. Let me just pause it for a second here because this is important. Up until this point, there's really nothing here that binds your design to a physical platform, a platform being a cloud, right? So at this time, what we've just done is that we've generating a heat template and commit this design into an OpenStack deployment. At which point you're going to have to start talking about VM, start talking about the kind of compute, storage, and memory requirement of the individual VM that you're instantiating, as well as the heat template that's necessary to deploy this whole shooting mess into OpenStack. Okay? So here you can select different flavor that is available in your private cloud for deployment. So for instance, you can, you know, say that this one particular VM that you see here on the upper right-hand side is of M1 medium flavor, and that would mean a certain amount of capacity in network and provisioning for this VM, right? Now, when you're all done with this, then the idea here is that you can just simply connect it into an OpenStack installation and onboard the design and have it be working. So, full disclosure, we don't support just OpenStack, but also public cloud like AWS. AWS, I'm sorry, it's a pretty long day. So with AWS, the model is different. They don't talk about compute in terms of VM, but it's all Lambda function, right? So it's just a set of callback function that get invoked whenever a particular event is fired. So retrofitting that model into a common design is a bit of a challenge, but we're making very good progress in that direction, right? Here you see we're generating a template for OpenStack, and we essentially successfully deployed it into an OpenStack, a running OpenStack instance. Okay, so you can click on the link that's offered there, and it'll take you to the OpenStack console, and you can see your network being deployed. Right? I came from the embedded background where we think of software development as host versus target, right? And if you think of the cloud as the platform of the future, then it's no different than an embedded target. You simply work on your design, you build the code, and you deploy it on the cloud. There should be nothing special about it that really forces you to do things a certain way. Okay? So, how does this fit into the Intel NEV? So, first and foremost, we can certainly put together a reference implementation for NEV services using the existing library and pieces that we have, simply by service chaining them together, okay? We can also encapsulate NEV services into VNF or microservices, and the benefit of that is that you have now effectively decoupled your design from the platform. So if you look at the picture on the left-hand side, which came from, by the way, V-switch is misspelled, so you may want to look into that. That's on the Intel website. But what you want is, no disrespect to the Wind River folks who basically outlay here an excellent platform to host the NEV services, but you ought to be able to take the same design and deploy them on, say, Red Hat Linux, right, or Ubuntu, or any other environment that can host this kind of functionality. Okay, so essentially, you can take something like this and realize it by dragging and dropping into Canvas, service chaining them, and just say go. The availability of tools like this is really directly proportional to the vibrancy of the ecosystem of developer. And you don't have to look any further than, say, Xcode from Apple, or Android Studio from Google, or Visual Studio from Microsoft as evidence of the fact that this type of strategy works, right? So access, ease of use, and availability is everything. Now, we'll pivot a little bit and talk about what we do with regard to characterizations and dimensioning for the mobile edge, but we're doing it at scale, right? Whatever that means, okay? So here's sort of a very high-level picture of the mobile network. You start out with the user equipment, and then you've got radio, the radio head, whether it's your millimeter wave, massive MIMO, or even your access point at home can be considered a remote radio head. All that stuff just backhaul into the IP core where all the real works are done. At least that's the vision, right? Now, of course, you also want to be meeting the 1 millisecond latency that 5G had dictated for you, and taking everything back to the IP core network and to the other UE is probably not going to work as a viable strategy, right? So what do you do? And that's really where mobile edge compute comes into play. So we have a set, well, it's really hard to describe what it is, but it's first and foremost a test socket for hyper-connected network. Right? We start out on the UE side by providing an environment where you can actually scale the number of user equipment in the thousands. Okay, and we're not talking about simulations or even emulations of user equipment. We're talking about real, actual user equipment that can actually bombard your radio head with actual data. And because we actually have something real that's running, we can now actually create a mix of workloads, not just phone to phone, but we can have phone talking to drone, or car to car, or you can have a smart venue or a smart meter type of a situation. List goes on and on and on. What we deploy out on the edge is very consequential to what's happening in the core network, because it puts a different kind of pressure on the network, right? So if you're using just all phones, well, the packet size are much larger and latency isn't a problem. When you're dealing with IoT devices, it's all 64-byte packets, and those things are the worst from a networking point of view, right? Those of you who have suffered this would probably attest to that. So anyway, what we do is we've got an environment that can simulate really close to what a real network will be like out on the edge. And then starting at the E node B and at the MEC node, we can introduce into it, whether it's FlexRAN or NEV SDK, an application that sits in between your E node B and the rest of the Evolved Packet Core. Right? And then in the core network, we've got a full set of virtualized services, starting with all of the virtualized Evolved Packet Core application, as well as a full set of session border controller and IMS services that can be deployed at scale. And when I say at scale, I mean from a capacity and latency point of view, it is on par with commercial offering that you see out there. So all of this is conducive to two things. One is it's a platform for you to do testing, both in terms of scale as well as in latency. But second of all, it's a socket where you can actually place your application into. Let's say you're developing, you say you're the poor chap who's been tasked to build a new version of the home subscriber system, right? Now, to test that, you actually have to have everything set up in a way that is getting all the stimulus and response from the rest of the network. And that's really difficult. You end up doing more scaffolding than really working on your application. By having access to something like this ready to go, you can just simply replace the reference versions of the HSS with your own and start doing business. You can debug through it. You can outlay this with different versions of your implementation. You can experiment with different hardware and see what sort of performances you get. All right? So really help to accelerate the maturity and the speed of the development of what you're doing. And I can show you a little bit of a video in terms of how this all works, right? So we started out by orchestrating this entire framework with a front end. So you can select and tell it what sort of services you want to deploy, whether you want to run IMS and session border controller or even voting on this thing. And then you tell it how many E node B you want to instantiate and how many UE you have for each E node B. And you say go. So we orchestrate now everything in the back end. And this thing comes online, right? So as it comes online, you see visualizations of different cellular area being covered by the 2 E node B that you've instantiated, and then there's an Evolved Packet Core that sits in the middle. I want to remind you that none of this is simulated or emulated. They're all real. I mean, you can take this and stick into a real network and actually go to market with it. I mean, with more work. But there's nothing about it that is not discrete. Okay. Now, those dots that you see there, so individually, each one of those is a UE. It's a fully functioning UE. So the color changes is reflecting the fact that these UEs are coming online. They're registering with the E node B. And you got indications in terms of how many active users you're having in this network, so on and so forth. You can scale this into a full city block if you want, if you have enough hardware to support it. And it's just a matter of more servers and data center spaces. And we'll talk about that actually a little later on today as well, if anybody don't boot me out here before it's too late. So when this all came up, let me just fast forward this in the interest of time. You can actually click on each one of those UE and telnet directly into the Linux shell that runs on them. And so that's just kind of proof positive that they're really, really a running system. And it's nice because then you have the opportunity to just kind of load anything you want on it and just go, run, right? So if you're trying to characterize the behavior of some IoT devices, you can load up an MQTT client and have it talk to an MQTT server that runs in the core network, or one that may be running inside of MEC. Okay, so pretty cool stuff. But moving on, let's see what we can do as far as MEC, right? So we put together a very trivial use cases where across the continent we have basically two UE talking to each other. And so this is the unoptimized case. One UE talk to the Node B, go back to our data center and come back to the other UE across the Pacific. All right. In the optimized case, we insert a MEC node in the middle, and we run a set of algorithm that detects whether or not the respective UEs local. If they are, we route the traffic so that they don't have to cross the ocean. And what you see here in the diagram is really the logic that runs inside of the MEC node. Okay, and then of course what we found out. In doing this is, no duh, you get better latency, right? Because you don't have to go very far to get to where you want to go. So it's an example of how MEC can be used to transparently optimize network performance, right? But we do something more substantial. So we say, look, now we've got this nice environment. How can we use it to help us better optimize performance of some of the pieces that we built? So we single out this service packet gateway. Actually, we were inspired by some of the work that was done by Intel people at the FDIO presentation, and we took the next step by putting a software packet generator against the service packet gateway in our deployment, and we were running a whole series of tests. Right? So what we were doing is to run it with or without container, in kernel mode versus user mode, and with different packet size, and the results are here. All right, so unsurprisingly, running thing inside a container is the fastest way to go. And not going to the kernel is most optimal, because interrupt latency will kill you. All right? So now, we've got all these nice ingredients, and I got to thinking about, well, we can build something a bit better than just a little simple routing application. So let's just propose something that is just really cool and really controversial that we can kind of latch our teeth on, right? So Neil Oliver from Intel brought this work to my attention. It was basically a project in the EU called 5G X-Hall, right? So they wanted to do a study of a district in Barcelona, and I have to be careful how I pronounce it. I think it's Eixample, right? It looked like a misspelling of example, but it's not. So Eixample is a district in Barcelona. It has about 500,000 in population. But what's really unique about it is that the layout of the district is very regular. So it's approximately 133.5 meters square for every block, which make it very convenient for you to situate about 5 small cells and 1 macro cell for every 1.5 blocks. Okay? So the traffic flow in this type of a situation would be from a small cell to a macro cell and then to the MEC node. And given the number of blocks in consideration here, you're going to need about 1 cell for every 100 person who lives in this district. Okay? To kind of give you the sort of dimension and the size necessary to go to deployment with something like this. So what's the epiphany? Well, here's the epiphany. What if we want to democratize mobility? Okay, this has been done many times over, oftentimes with either dramatic or disastrous results, right? So if you look at, for example, hotels, Airbnb is a democratized version of that, and say, you can rent out your own room. You don't need, to rent it from a centralized entity that's called hotels. Taxi, Uber, and Lyft. Some of us may be taking that to go home today, right? Banks used to be centralized lending institution. Nowadays, you've got lending club that get money from A to B in a peer-to-peer fashion. fiat currency. Has anyone here heard of Bitcoins? Right? So it goes on and on. But what is there for telcos? Okay? Can we decentralize the whole business of telco? And in doing so, taking full maximal advantage of what MEC has to offer. Right? So I took a look at this district in Barcelona. Right? So started counting the number of bus stops that's there. And I went and started counting. By the way, all this data was brought to my attention by Neil Oliver, who is a stickler for data, absolute stickler for data. But that's just an aside. So you've got so many different car parts where you presumably can put access point or even small cell on. And then of course you've got lots of Wi-Fi hotspot. Okay? So suppose, before I go to the next slide, anyone here have heard of FidoNet or remember what it was? Okay, so you're a lot older than you look, right? But so it's a punchline. What if you were to create a service called FidoPhone, right? It's tempting to call it Fidophonica, but considering we're doing this in Barcelona, it's a bit below the belt, so we're not going to call it that. Let's just say FidoPhone. All right? So with FidoPhone, you bring your own mobile wireless infrastructure into the picture. So you're your own radio head, you're your own access point, you're your own front hall. Okay? People that come within the vicinity of your access area pay for it on a per use basis, right? MME and service packet gateway and everything else is all distributed. Okay, so is this possible? Okay, so let's look at the viability of something like this. Issue resolution. So first and foremost, you need a license to run a telco. I mean, there's only about 700 to 1,000 telcos in the world. That's for a good reason, because it's really hard to become a telco. You got to go through heaps and heaps of, regulations and approval and whatnot. Not to consider you have to be very deeply pocketed to be a telco. So not a whole lot of people come into the picture. It's not on a daily basis that you hear about such and such company, being a new telco. Maybe with the exceptions of Reliance Jio. And when they do it in a big way. Anyway, but you can avert this by decentralizing everything. There's not a central service. Uber, by all stretch, is not decentralized. There's still the Uber server that tells driver where to go pick up people. To truly have it decentralized, you can't really regulate such a thing because there's no one to actually go after, right? I mean, look at Bitcoin, for instance. We'll talk a little bit about that. But what about centralized data? What about things like phone numbers and mobility informations and things like that? Well, the crypto people figure out how to fix this problem. They have distributed ledger that gets synced on a frequent basis, right? So eventually all the usage data and all the billing data is going to be everywhere. And there are protocols that you can use to make sure that they're always staying updated. So this is not a problem. This is a solved problem, okay? What about compute and storage resources? Whether you can find enough compute and storage resources to do something like this. Well, guess what? Those existing access points that you have in your home, they run Linux, right? And lots of them have already been rooted to run things like OpenWRT, which is really Linux with FreeSwan IP table, on top of them. They are hugely programmable, and they'll make a perfect edge device, right? Now, they may not have enough storage, but it's not beyond the imagination to have, 1 out of 100 households buy their own personal Xeon-based MEC node and operate them, right? So, not too far-fetched. Then you still have to ask the question, well, who want to do that, right? What's the incentive for doing that? Well, you get paid. You get paid in micropayments. You get paid with cryptos, right? You probably have read about people buying ASIC mining rig to mine their own Bitcoins. And those things cost a lot of money, probably as much as, well, not as much, but maybe less than a Xeon-based MEC, right? The point is they get rewarded for that. And if there's a way to financially motivate the individual to run one of these things in their home, they will. right? Now, if you're able to get every single person in Barcelona, or every other 100 person to buy a Xeon-based MEC node, I think that's a pretty good thing. Both in terms of the technology as well as for the hardware enablement. It goes into it, okay? So now you're thinking, well, can I use Bitcoin for something like this? And full disclosure, Bitcoin isn't micro enough for something like this. If you do some lookup, you can find that Bitcoin do typically about 300,000 transactions a day, right? And that's really what goes on. In comparison, eBay handles from 2 to 3 billion transactions a day, and they're not even micro transactions. I mean, that's thing, for the large thing, not small transaction like a phone call, for example. So, it's problematic, but there are other solutions for crypto that would fit this model quite well. In the process, also reward the operator, the individual, for providing the infrastructure to make it all work. All right? And what about billing? Well, you don't need billing if you can actually transact everything into blockchain and ledger it into your network, because you get paid on demand, right? People use your mobile network, they pay for it, and a question. All right, so something to think about, yeah? So in summary, we talked about Terranium, which is a DevOps IDE that we provide for the telco cloud as a means of providing an environment that is accessible and easy to use and customizable, all that good stuff. And the applications and the components and the VNF that we build in Terranium get put into the service we call PinBub. It's short for Binary Republic. Right? So think of PinBub as a binary versions of GitHub. Right? But when you've got your VNF in there, well, we make sure that it's characterized against a bunch of other VNF, and we can tell you whether they're compatible and what sorts of capacity that they can offer. So pretty good, right? Now, Validium is what we offer by means of a private test and characterization cloud. So sure, you can use AWS, but if you have very specific needs in terms of your orchestrations and your automations and all of these VNF that you have to stand up yourself, we can offer it to you turnkey and just go to work, right? And then last but not least, you've seen the Dronova end-to-end testbed as well as reference design that sort of fit everything together in one big puzzle. So that's my talk for today, and thank you. Okay. So any question before I turn it over to Jeff? Okay, cool.
That's a very cool project. Thank you. The question I had was on your the first MEC that you were talking about, where you were able to intercept the S1. So did you terminate the tunnel there, or what did you do about that?
Well, that's the prerogative of the application, right? So the application can decide to terminate it. I mean, for example, it could decide that it was a raw packet and just kind of send it into the reject bin. It can modify, it can DPI it and just keep sending it on. So just think of it as a bump in the wire. I left my, but certainly it's not, thank you. Our philosophy is not about defining a rigid set of API that people should be using when they're building their MEC, right? Think about days of compiler optimization. When the first guy that came out and started doing this for 6840 or 6820 or even the 8800 microcontroller, he doesn't know what other processor and what other instruction set is going to come after it. So he does the best job he can for that particular instance. And the more and more these things he does, then patterns starting to emerge. And then now you can start building API. So I see API as a consequences of experience, not the other way around.
And what is the UE emulator that you had?
It's the full instances of Linux. In this particular case, they're all containers.
Right. And what is the backend that it supports? Is the OAI open air interface, or what?
It can marry into OAI or any other evolved packet core framework that you can put in there. We started with OAI, but then we've done a huge amount of work to componentize it, to virtualize it, and to optimize it with things like DPDK and DPP. That it, in fact, quite a far distance from where we started.
What is the name of the product?
It's a pre-launch service. We call it Dronova. It's in honor of Lord Drona, who's the archer for Arjuna. Yeah, so he's an archer, and this is about wireless and millimeter waves. I don't know if you get the.
So how would you democratize the allocation of spectrum? About the last.
We don't. I think.
Did everybody hear me?
Yeah.
Okay. Oh, you have this right. Yeah. So going back to your last part on slide, how would you democratize the allocation of spectrum?
Well, we don't. I mean, that's kind of again it's above our pay grade, right? But what we do know is that 2.5 and 5 gigahertz range for Wi-Fi. That's public access. And nowadays you also have things like CPRS radio frequencies open to public, right? So over time you'll see more and more of these little slots that you can take advantage of in order to mesh together a network that can make these things hum. The reason why it hasn't happened yet, in my opinion, is the misalignment in incentives. You don't incentivize people to do certain things, but the right incentive isn't there, people simply won't do it. This whole thing with crypto being the way it is actually plays really well into this narrative, because all of a sudden, people do want to own this crypto because they're worth something, right? So by rewarding them with that, by having a mean to actually allowing them to get paid, really motivate people to make the time and resource investment in doing something like this and making it really work.
Any other questions? Okay. Oh.
Slightly on topic, but how does Hashgraph fit in with this concept? I know it's blockchain overall, but I didn't know if do you know anything about Hashgraph?
I do. Well, somewhat. We tend not to want to take a side, right? So there's a lot of smart people in the crypto community, and I think the Hyperledger organization, I do think from a resource point of view, have a lot of weight behind them. But we do know what an environment or a system like this will need. And it needs the kind of fine granularity that isn't there today with crypto, right? Simply because of the way that it's being mined and all that, which I fundamentally think is regrettable. I try to abstain away from taking those positions.
I was just going to say thank you.
Thank you. So now we have Jeff from Wind River.
Yep.
All set? Awesome. Great. All right, good evening, everybody. I think I'm batting cleanup tonight, so look at me. I'd like to thank Intel and our hosts for inviting me to speak this evening. I have to tell you, I wasn't quite sure what to expect in tonight's meetup. In taking a look at the presentations that I missed earlier and in the last one, it looks like you guys got a lot of information around NED SDK and MEC and sort of the how and the what. My presentation is going to be more focused on the why for multi-access edge computing. Part of that is just because of my skill set. So I'm a marketing guy, but I promise not to bombard you with a bunch of marketing slides. But I do want to give some context into sort of what we see as the real drivers for multi-access edge and what we see as some of the unique requirements for multi-access edge and some of the use cases. So I'll talk about the business case, I'll talk about some of the use cases, and I'll give you an example of a ready for deployment platform that we built together with Dell EMC and Saguna. I'll also give a little introduction to Wind River. I'm assuming there may be one or two in the room who don't know who Wind River is, so making sure that, oops, sorry. You know who we are, and then if time allows, I've got a brief demonstration at the end. So let's just jump in. So some of this is probably going to be recap from earlier. So what is multi-access edge? So it's bringing the content and the application of data centers into the RAN. So providing a virtualized cloud computing environment, getting it closer to the consumer, and thus enabling new services that wouldn't be feasible with a with cloud-hosted architecture. So that's kind of the what, but then let's talk about some of the whys. So from a service provider perspective, where we see this being important is that MEC can provide for new revenue streams and potentially new customers. So this may be with the industrial or enterprise customers, and it could be with consumer customers. It also gives service providers an opportunity to penetrate into new markets. So when we think about new markets, we're thinking about medical, thinking about sports, thinking about industrial and automotive, so some new places for service providers to play. And then MEC also provides a framework for accelerated deployments. So getting your services out faster, leading to larger market share earlier. So what I'm going to do is I'm going to walk through 4 use cases, and these are use cases that we hear our customers talking about. These are things that we hear from service providers in terms of areas where we think that a MEC deployment might be most relevant. So the first one is for something like a stadium or other high-density locations, so new small cell services. So if you think about when you go to a sporting event today, you've got this large venue that most of the time is sitting empty. I mean, I drove by Levi Stadium, there was nobody there, of course, when I came here today. And then all of a sudden, when there's a sporting event, you've got 10, 20, 30,000 people who are all of a sudden converging at this one location. Everybody has their phones. And so imagine if you could go to a sporting event and the folks with their phones could do things like see an instant replay on their phones, or perhaps they want to see a different angle of the play, or perhaps there's drones flying over that provides them a different view. So those are things that you can get from a user experience. Maybe I'm sitting in my seat, I'm thirsty, but I don't want to stand in line because I don't want to miss the action. So I could take a look at my phone and find out which kiosk can get me my beer faster because there's no line. So those are the kinds of services that we think you might be able to provide to a consumer at a sporting event. Likewise, the MEC infrastructure also provides for things that can enhance security at the event. So the ability to use facial recognition software and see if there's any bad actors who are looking to cause trouble at the event. Likewise, the stadium owners or the service providers can then use that infrastructure to push relevant information to the consumers and to the attendees of that event. So perhaps there's a coupon, or perhaps there's messaging that they want to get out to the attendees. MEC is a good way to do that. And without a multi-access edge sort of localized cloud, all of this information would have to go onto the backhaul. This way, you can keep that information more localized and not put the additional strain. So example number 2 is actually a few different examples, but I put them together on this slide because they're related. So the first is augmented reality and virtual reality. So you know, there's a big push and there's a lot of excitement around AR and VR in the gaming world. Certainly every conference that I've been to over the past year and a half, there's at least one vendor who's got the AR goggles or VR goggles, and they've got some really cool display. So there's definitely an opportunity in gaming, but I think beyond gaming, we're seeing interest in particularly augmented reality in things like maintenance and you know, if you think about sending a technician on site to fix a certain piece of equipment, if they have augmented reality goggles, that can help them identify the problem and fix the problem much faster, potentially, than having to rely on their memory or having to look up on their phone or look at a manual. So, you know, that kind of thing can be very, very helpful in that part of the world. And then on the other side of the screen, we're talking about tactile internet, and that's really around use cases like telesurgery, remote medical diagnostics. You know, I actually recently had a personal experience with a family member and a friend who both had to go to the emergency room, and they used robots to work on their body, which I think is, you know, such a cool thing of the future. But with multi-access edge, you know, that enables that kind of technology because you have millisecond response times. It's very sensitive equipment that you really can't afford having any lag. So I think multi-access edge is something that could really be applied in the medical and in the medical world. The next example is where we get into things like driverless cars. So when you're talking about vehicle to vehicle or vehicle to infrastructure communication, I don't know about you, but when I'm going to be driving in a driverless car, I want there to be zero lag time for when the car decides that it needs to brake and when it actually brakes, right? And what I really don't want to have happen is if the car needs to communicate back to infrastructure, you know, I don't want the car to have to reboot in the middle of the freeway, right? So that availability, that low latency, that high bandwidth, you know, those things are very, very important when we get into a driverless car. And then one thing I haven't discussed yet is security. So security for multi-access edge is paramount. If you think about a data center, chances are you've got a big locked building, you may even have an armed guard, so there's plenty of physical security in that building. But if you've ever seen a central office, you know, some of these buildings are really not much more than a shed with a padlock. So in terms of physical security, there's not a whole lot there. So if we're going to put this type of infrastructure out at the edge, which is what we're talking about with multi-access edge, that security has to be built into the hardware, it has to be built into the software. So again, no bad actors can get to it. So far, each of the use cases that I've talked about have kind of gotten incrementally more, I don't want to say important, but the requirements have sort of amped up because of safety requirements. This last one is really critical, which is HD video and premium television. So that was a joke. I don't know about you, but when I'm looking on my phone and if I'm pulling up a video, whatever that video is, if there's a lag time, if it takes too long for that video to load, or if I'm watching the video and it keeps cutting out, chances are I'm going to bail. In fact, and it sounds like I'm not alone because it looks like a 1-second rebuffering event during a 10-minute premium service clip will cause a 43% drop in user engagement. So this is big. You don't want your customers to drop your service and move on to something else. If you have their attention, you want to keep it. So being able to deliver video and using multi-access edge for things like transparent content caching, for bandwidth guidance, that sort of thing, to make sure that premium delivery is both quick and smooth.
Could you go back to the first example?
I'm sorry?
First example, the first one, first slide.
Sure.
Is this service already deployed?
I'm sorry?
Is this service already deployed? Any sports events?
It may be. We don't have a service deployed at a specific stadium. I'm not sure about other vendors at this point. So just a quick overview of the value chain. So really the point of this slide is to illustrate that there are a lot of people, a lot of entities who both stand to gain and receive a tremendous amount of value through these MEC use cases. So whether that be the component suppliers like Wind River, Intel, and probably some of you in this room, the infrastructure providers, the content providers, and then of course the end users and consumers. There's a lot of value to be gained here. But there are some challenges, right? So, sort of paint the picture of what a wonderful world will be with MEC, but there are some significant hurdles to overcome before we get there. First of all, we're talking about new technology. So just inherently in being new, the folks who are building this infrastructure, the folks who are deploying this infrastructure, they're really paving the way, and they're kind of figuring it out as they go, and there's going to be some growing pains along the way. The integration for an end-to-end solution is very, very complex. I'm sure that there are some providers out there who would love to be the provider of technology for all things telecommunications. But before that happens, we're going to have to play along, and there's going to be a lot of different components that are going to have to work and play together. So that integration is very, very complex. And then on the technical challenges, really most of these are a copy and paste from the auto slide. So ultra low round trip latency, must have high bandwidth, high availability is very important. You need to have a full comprehensive software stack, and then robust security, as I already spoke of. Wind River has worked with Dell EMC and a company called Saguna to put together I guess you could call it a reference platform. So of course, Dell providing the hardware, and I'll talk a little bit about the Dell and Saguna components in a moment. And then Wind River providing the cloud infrastructure. So we provide a network virtualization infrastructure software platform, which is a bit of a mouthful, but I'll break it out here in the next slide or two. And then Saguna provides the Mobile Edge middleware. So that's one reference platform that we put together. We also work with a number of other ecosystem partners, which I'll show you a slide of who that includes here in just a moment. But folks like Affirmed, Altiostar, Astria, and Huawei all provide different MEC components that can also serve some of the use cases that I already talked about. Now these next two slides are not my slides, so I'm not going to go very deep, but I just wanted to include these in the presentation so you could see what we used when we put together this reference platform. So we worked with Dell. They have a couple of series of servers, so they've got their 5000 series and then their R series. We've validated with the 5000 series the R730, R630, and R430 for MEC and other use cases. And by the way, these slides will be available so you can read the details later. And then on the Saguna side, we validated with their two products called V-Edge and V-Gate, which again provide the MEC applications running within the RAM. All right, so let me back up just a little bit. How many of you are familiar with Wind River? Oh, quite a few. Okay. How many of you know Wind River for telco? Fewer hands. Okay, that's about what I expected. Every time I go to a trade show, I'll talk to somebody and they'll say, "Oh, you're from Wind. What's that?" I'll say, "Well, have you ever heard of VxWorks?" "Oh, yeah. 20 years ago, I worked with VxWorks," and typically the conversation goes down that road. So let me just give a quick recap. I'm going to just go ahead and build that out. So Wind River is a software company. We've been in business a little over 30 years, and as I mentioned, we're probably most well known for our product called VxWorks. So it's a real-time operating system. It's used in a lot of different areas. We have a strong presence in the aerospace and defense, in industrial and medical applications. A little fun fact, we have 100% market share in real-time operating systems on Mars. So, that's a little tidbit I like to throw out at parties. So we have a long history in those areas. We also have a long history in telecommunications. So VxWorks, our Linux products, and our Titanium Cloud products are used by the top 20 telecom equipment manufacturers worldwide. And we have products that span, that are applicable throughout the network, so anywhere from the core out to the edge. We're very involved in open source communities, consortia, and groups. And our Titanium Cloud product is really built to address 4 key business challenges. So I realize that the text is very small over here on the right, so I'll just summarize it. So number 1 is protecting top-line revenue. So we do that through our high availability, ensuring that our customers have reduced churn, reduced SLA penalties. Gaining market share by accelerating deployment of new services. So that's really part of the promise of network functions virtualization, is to be able to get those services out there quickly, and we enable that through our platform. Minimizing the lifetime operational costs of the networks. So we do that through simplifying our installation, our operations, and our management. And then that's also done through our some of the technology I'll get to in just a moment that makes our product run very, very efficiently. So there are fewer cores required to run the virtual machines that telcos would want to support. And then leveraging open solutions to mitigate the risk of vendor lock-in. So our products are based on open source. And then we do a lot of validation to make sure that they are interoperable with other products. So let me just speak a moment about Titanium Cloud. So this and the next slide will go through kind of a definition of what Titanium Cloud is. So at a high level, it's a network virtualization software architecture. It comes in a couple of different flavors. We've got Titanium Core, which is the product that we've built that's targeted towards the data center. So it scales anywhere from 4 servers up to hundreds of servers. We have Titanium Edge, which takes the features of Titanium Core and shrinks them down into a 2-node deployment. And then we have Titanium Edge SX, which would be used for far-edge single-node deployments. We also have a relatively new product called Titanium Control, which I'm not going to spend time on in this presentation, aside to say that this is our product that's really designed for industrial applications. So we're seeing a lot of interest from our industrial customers in virtualizing and consolidating their equipment. And so Titanium Control is built for that market. Yes, sir?
So Titanium Control software runs the way of PLC?
I missed the last part.
Where is this Titanium Control software runs? It runs in a factory?
Correct. Yeah, so our,
Hello.
yeah.
The Titanium Control software runs in the PLC in a factory?
Right, so it's to virtualize the factory operations. That's correct.
That would be very interesting, actually.
Okay. So all of the products that I just mentioned are built around this framework and these components. So Titanium Cloud comprises everything that's in the red box here. So we start with open source components, start with OpenStack, Linux, Ceph, DPDK, and then we sort of build up from there. So we add real-time performance enhancements to KVM. We have our accelerated virtual switch, which is based on DPDK. That's a key component in the performance and the efficiency that I talked about. So with the performance of the virtual switch, we get 40x the performance that you would expect from open virtual switch, which means fewer cores supporting far more virtual machines. We also add plugins and extensions to OpenStack around our carrier grade piece. So that's the high availability. So things like the ability to do live migration, hitless upgrades, that sort of thing to keep systems up and running at all times. All right. So these next few slides are just kind of. Yes, sir.
Is there any optimization for Ceph storage?
For Ceph?
Any optimization for Ceph storage?
You know, to be brutally honest, that's a piece that I'm less familiar with, but I can get you more information on that if you'd like. Yeah.
How about the virtual switch? Is it open flow based?
So the accelerated virtual switch is a proprietary piece of software that we developed based on DBDK. It's compatible with OVS, but it's not OVS.
How do you configure? How is it configurable?
So I'm the marketing guy. I'm not going to be able to answer that question. I'm sorry, but I can. If you give me your information, I can get you that answer afterwards. So kind of going back to the flavors that I talked about. So the titanium core scales from 4 up to hundreds of servers. So this includes the high availability, so 6 nines availability, simplified installation, high performance, very, very low latency. And then the dual server, the Titanium Edge, all those features, but shrunk down to a 2-node deployment. And then, as I mentioned, the single server edge. So this provides all of the low latency and high performance that the other provides. Of course, we don't have a second physical server to fail over to, so some of that part of it is limited. How am I doing on time?
Yeah, we'll put 17 minutes.
Okay, thanks. All right, so I mentioned how the product can minimize costs, operational costs. So a little more detail around that. So it is delivered as a single pre-integrated image. So it's the operating system plus OpenStack plus the virtualized infrastructure manager. So you can deploy it to all nodes without intervention. The in-service software upgrades and intelligent orchestrated patching engine, so that's all done through Wizard or REST APIs, and then the comprehensive system visibility and alarms is really geared around making sure that the operators know what's happening in the network at all times and are able to mitigate issues as they come up. A really key part of our story, so of course there's the technology which we're very proud of, but we recognize that the technology of Titanium Cloud in and of itself may be interesting, but not that useful on an island. So that's why we developed our Titanium Cloud ecosystem a few years back. And while on one hand, the ecosystem is certainly a marketing effort, so we've got our logo list, which I'll show you in just a moment. Behind the scenes is an in-depth engineering effort. So we get our smart folks to work with our partner smart folks to make sure that the products that we're working with not only work together, but are also optimized and are doing what they're intended to do in a network environment. And so just to show some of the partners we work with, I would say that we're fairly hardware agnostic, working with most all the major players. We've selected the VNFs really based on best of breed in the industry and customer requests. And then of course we work with OSS and BSS vendors and orchestrators as well. More recently, we've added InnoCybe as our first SDN controller partner to our network, and then also, of course, working with some of the system integrators. So I think this view of this slide is fairly interesting, but I think this one may show a little bit better who we work with and what they do. So as I mentioned earlier, work with Saguna and Multi-Access Edge. ASOX is another firm that provides MEC-specific capabilities. And then, of course, there are the other folks that I mentioned earlier that were in the previous slide. So what I'd like to do, the folks at Saguna put together a demonstration. It's just a quick video just to illustrate what a MEC environment can do versus an environment without multi-access edge. And so in this particular example, it's going to show us what bandwidth guidance can do. Let me just build this out here. So I'm probably preaching to the choir. I'm guessing most of you folks know a lot about this already. But the basic notion is from the user to send information back into the cloud so that the server can deliver the right content to the right subscriber, thereby resulting in a better user experience and a smarter utilization of network resources, which I think that part is really key.
So, what is over TCP header?
I'm sorry?
What do you,
Over TCP header?
yeah, what do you mean?
I was afraid somebody was going to ask that question, and honestly I don't know the answer. I feel like I'm batting about 100 on your questions. I apologize for that. So in this demo, data is sent up to the content delivery network, and basically will send information to help smooth out the flow. So if you look at the left side, you've got a steady bit rate of 3 megabytes. On the right side, it kind of jumps around, so we're down on, okay, now it just came up to 5 megs. This piece was all done by Saguna, so if anybody wants to ask what all this means, I'll have to get back to you on that one. But really the idea behind this demo is to demonstrate with some sort of bandwidth guidance, the content can be delivered at a rate that smooths it out, doesn't cause the video to be jumpy. Whereas on the right-hand side, you can see, it'll play for a little while, it'll stop, it'll get caught up. Honestly, this is really much more like what my typical experience is when I pull up a video on my phone. Anybody else have that experience? One? Okay, a few more. So anyways, it's really just to give an example of what the world might look like if we were able to push that content closer to the edge and really provide that guidance back to the network in order to deliver this content in a much smoother manner. All right, so to wrap it up, so I talked about a number of different use cases around multi-access edge computing, kind of giving some of the why, sort of why behind the technology. I talked about some of the requirements that some specific requirements that those use cases will demand. I gave an introduction to Wind River and some of the components from our partners. And really at the end of the day, when we talk about why multi-access edge computing, there's the opportunity for improved top-line growth for a service provider. So that's through new services, new customers, accelerated deployments. There's an opportunity for major operational cost reductions. Reducing penalties due to service downtime, so that's part of the high availability that we can provide. Simplified installation, commissioning, and maintenance, and then the reduced overhead for control and storage. And then, of course, a proven solution from Wind River, Dell, Saguna, and our validated partners will certainly mitigate risk. Not to say that somebody can't go out and build this, but when you go with a proven solution, you don't have to. So I'm going to stop there. I'll take questions. I won't promise I can answer all of them, but I'll certainly be happy to get anybody's information if I can follow up with you. Hopefully I didn't scare people off.
Thanks, great presentation.
Thank you.
I'll give you a marketing question.
I love marketing questions. I might be able to answer it.
I read an article about Google Glass being used heavily in China with police agencies doing, face recognition and bringing up licenses and stuff real time. I would imagine that probably some kind of MEC would be quite helpful there. Do you know where Wind River intersects with applications like that?
Yeah, absolutely. We're actually working with a customer on a prototype for that exact use case. So for a police officer to use their camera or Google Glass or whatever the apparatus is to be able to do things like read license plates, identify perpetrators, scan the situation. So, I think that it would be, from the Wind River perspective, that would be a combination of sort of MEC components, and we also have a number of IoT tools. So that's where a VxWorks or our Helix device cloud sort of device management for that kind of a service would come into play. So yeah, I mean, I think it's early days, particularly in the US, but we are seeing some interest for that kind of use case. And I do think that would be a great example of where MEC could really help out.
Thanks.
Thank you. Look at you.
I was going to use it in a scary way.
I know, yeah. Any information coming up about me? Yeah.
Well,
Yeah. Apprehend that man?
That's got to be good.
Okay.
Oh, it's off right now.
Okay. All right, so I'll be around for a few minutes. If anybody does have any questions or follow-up, things that you may want to ask now but are afraid that I won't be able to answer them, please let me know. I'd be happy to get you that answer. That is my job. And thank you very much for having me. Appreciate it.
Thank you, Jeff. So now it's time for some fun.
That wasn't fun?
No.
Okay.
You dressed up. Come on, this was fun. We were debating on the dress code today. So Jeff decided to dress up.
To not go with the Tongan style?
Did you tell them at the survey?
Yeah. So we have a survey open right now.
Yeah.
And we have a prize for that. That's Amazon Echo. Echo Dot. That's the prize if you fill up the survey. So idea roulette cards. Do people have that? We have 2 DPDK box kits that we will give away. So anybody ready to come up with their project ideas? It's just an exercise to go wild. It doesn't have to be practical, implementable, or anything like that. Oh, okay.
Hi, my name is Sunil. I have a project idea for a network function. One idea is to have different types of traffic based on policies. It could be, say, video traffic going to a video optimizer, and captain classifier. It could be another network function. So this can be dynamically configured both at the consumer level, and also it can be done at enterprise level.
Sorry, I missed that. The word is. Can you just repeat?
Yeah, no, I was saying that for network function virtualization, I'm most talking about service chaining different functions. It could be like a firewall, video optimizer, and policy, and this can be dynamically configured either at the consumer level or at the enterprise level. And it can be at application level service chaining, or it could be at a network level service chaining also. Oh, my idea on that is basically how it interoperates between the application and the network. So it can be used using metadatas as one way where different layers can communicate in the service chaining. Because that's one of the things when you talk of interoperability between vendors. So that's something to think about.
Something like NSH, except for the orchestration and management versus sending traffic from one VNF to other. Okay, yeah, thank you. Michelle, does he get a... Yeah. So people on the stream, feel free to log off now. Thank you for joining us. We'll be having some fun here. So next time, hope to see you here. So from people in the room, any other ideas?